So I'm gonna explain somehow about time projection chamber with liquid argon fill in it. So because we have data that we are gonna work on it, it's Lariat data that I generated for different particles. So we can do the files and everything are there. So let's go through and explain what's the data look like, and how we get the data, and then we can, if everyone has lab 3, we can go ahead and start the exercise in lab 3. So what's the liquid argon time projection chamber and how it works? Actually, when the particle from the beam comes to the detector that is filled with argon, the particle interacts with the nucleon inside of the argon. So the interaction gives us the different particle. For example, neutrino hit the nucleon and give us pion, muon, and stuff. So the particle with positive or negative charge ionize the particle on the way through. So we have the electron as a result of the ionization. So if we employ the uniform electric field, we can drift the electron and see the electron inside the wire which is shows with pulse in the wire. So electron goes through the detector, ionized particle, we drift the electron from the ionization, so we see pulse on the wires. So there are 3 different direction that they put the wires to detect the electron from ionization. And the purpose is because to see the 3D information. If we have like 3 different direction of the pulse, we can project back and tell where is from and what's the charge inside, the produced charge inside the detector. So the thing that is read off from the wires is the amount of charge and the drift time that is projected back into the volume of the liquid argon. So we can say that the topology that we see in the wires. For example, imagine this is I'll show you the event display. The event display is the wires, number of wires, to the time to the number of wires. So each wire has a pulse. So each wire shows charge in different time. So if time goes in this way, I'll show it with the array to the right. So the particle comes and create the pulse in the wires during the time. So if we see the time over the wires number, we can tell what's going on inside the detector. And if we view it with different direction, we can say that, for example, in 2 directions, we can project back and give the information on 3D. And so the electron is drift toward anode in different 3 wire planes, and 2 first is induction plane. So we configure the electric field on 2 first wire plane that induce the charge inside of it, and then from the last one we collect the particle. And the purpose to put the induction is because we employ the uniform electric field. if we directly put the wires, anode wires in front of that, it's gonna destroy that uniformly. So we don't get the electron actually comes from the particle and we destroyed it. That's why the purpose of the induction plane is. So for the lariat that we are using, its data, they are using actually one induction plane and one collection plane. And one of the induction plane is off for the lariat. So we have two different images from induction and collection. And lariat actually is argonaut that get a second light. So we put it in the beam to Fermilab. The proton hit the target, produce the pion, and pion goes to the detector and interact. So the purpose of lariat is to see to get the idea how liquid argon interact with the different particle from the beam. So to get the idea of how liquid argon works. So this is the actual event display that Argonauts see in the online observation. So if you look at the top one is the induction and the bottom one is the collection plane. And the Y it shows the time, drift time, and X is the wire number. So by increasing the drift time, you see the different charge in the different wire number. So it gives us the idea of where the charge is and when it's produced inside the detector from both planes. So, and different particles, as you know, interact differently. For example, if you imagine that we have an electron interacts with the nucleon, it has different interaction than the proton, for example, because electron give us tampon, I don't know, diffract and create the photons. And the photons goes to electron, electron goes to photon, photons goes to electron. So the photon and electron give us lots of this kind of tracking, which is called shower in the detector. So, and if you think about it, if the particle doesn't have charge, if it goes through and doesn't have any interaction, you don't see anything in the detector because this is the charge. And the neutral particle doesn't create anything unless they interact, create charged particle. Also the same thing happened to photon. So if there's photon, you don't see any track, but lots of shower because it goes to electron, back to electron. That's why we have like this kind of track with short change in direction, which is called shower. And the proton is the highly ionizing particle because it's heavy and carry more charge than electron. Because it's heavy, it's gonna affect the nucleon more. And it has more interaction with the nucleon. So if there's a proton, you see a particle that the track that is straight, it's like high energy that it shows with red. For example, this is proton. And the muon it doesn't interact very much. So if you see the track, but it has charge. If you see a long track in the detector that it doesn't have like lots of energy, that it shows here with light blue, it means that it's the muon without interaction passing the detector. And also pion has lots of interaction that may happen to that. So liquid, the lariat is the main purpose of lariat is computing the cross section of pion inside the liquid argon. That's why most of the event that is seen in the lariat is pion. But the way that we create the particle in the lariat, we force it to produce the particle that we want. So I generate all the particle, even neutrino, and force the neutrino interact in the detector in the geometry of lariat. But lariat is not a huge detector, can show the neutrino interaction, because neutrino is like particle that has the small cross section. So we need a huge amount of material in front of the neutrino to see the interaction, but lariat cannot do that. So, any questions? And this is the, let's look at the electron and pi zero. Actually, if Dr. Farvin just told me 2 hours before class that I should present today. If I know it before, I generate more plot for you to see the different, the different picture for different particles. But I see electron and pi zero as useful because there is lots of conversation, and the people are, this is just, the problem, because they are trying to separate electron from pi zeros. Because if you see the picture, the 2 first lines shows 2D, and if we project back, we can get the 3D information with the actual the place inside the detector that things happen based on the charge that is ionized. So you see, who can say the difference between electron and pi zero from top and bottom?
How soon it interacts?
But
How deep in the detector that it interacts?
yeah, but you see the difference of the picture. Do you see any difference? Where?
What, one shorter?
What are the axes again?
This is the Weyer's number, and this is the time, drift time. The time that takes from particle to go to the wires. I'm not care about the, what it is. I'm just asking what's the difference between image top and image bottom. Well, can you see the difference?
Pi interacts with more wires and interacts more than the electron number.
The pion penetrates deeper into the argon because it's a much heavier particle.
Yeah, but I'm not asking about the physics. I'm just asking about the image. Just look at the image. If you see the 2 different, 2 dogs with different, for example, one with long ears, one with short, you see that, okay, it has short, this one has long. I mean, what's the difference? How do you, difference between these 2 with these 2?
There's more blue in the pion.
There's a
Yes, but it's possibility that it happens for electrons.
So is this not consistent? Does this
It
look
is,
different?
yeah, it changed. It changed for sure, because the points that particle interact with the detector is, different points. That's why, that's why it's challenging. Even with looking the plot, it's challenging to say the difference between electron and pi zero. But you know, if you see that the electron has like a line, but pion start from showering. See, but it may be because of the resolution we don't see this separation, right? It's like goes on top of each other, and we see that like this. So that's the challenge. So with okay, go ahead.
Why is there like with the electron there's
It-
straight and then it breaks and then there's like a little.
Yes, because pi zero it doesn't have charge, right? It goes without any interaction till interact with the nucleon and create like photons or whatever. For example, if pion interact with the nucleon and it can, you know, this is, for example, electron. If it has energy to, you know, take it off, this electron can have the sign inside of it, but pi zero not. And then if it has more energy, if pi zero is carries more energy, they can go through and hit the nucleon, and then nucleon goes to create lots of pions, electrons. Make sense? That's why after this nothing, we see showering, lots of electron and photons. So this is a challenge. And the experiment that I'm working on right now is just it's oil detector with just photon multiplier to see the photon from the nucleon or from the neutrino interaction inside the detector. After that, they see that they couldn't separate pi zero from electron. So maybe there are just misunderstanding what's happening inside the detector. So they design liquid argon with high resolution so they can separate pi zero and electron. And that's why mini boom goes to macro boom and macro boom goes to doom with huge amount of liquid argon.
What's the color indicate?
The color is from blue to red, it's the energy, the charge. So the reddish is more energetic. Like previous slide, if you see. It's done.
So those of you who aren't in the physics department might not know this, but the guy who actually invented the TPC works here.
Yeah, no, thank you. Yeah, I just want to say Dr. Nygren is the one that designed the TPC. And everyone is using, like, you know, it's amazing. It's amazing.
If you ever see him, like, trying, like, he's a brilliant guy. He'll blow you away. Like,
Yes, it's
Just
amazing.
good to talk to. It's not such a pleasure.
Yeah. UTA is, you know, lucky to have him here. Yeah. And if you see this is showing the joule. That's why it's proton. And that's why it's neon, because of the energy that's because of the charge that put in the detector.
Are you saying that the charge determines what it is?
What it is.
Okay.
Yeah, and charge and also the shape, right? From this, you see the shape different, right? You cannot talk about the charge here because it's shower and you have no idea what's going on inside, right?
So like in the top picture for the electron, like with like there's a streak of red and there's a streak of green, a little bit of orange, and then another red. Is that just different? Are those just,
Oh, okay. You're talking about this red?
right?
Yeah, this is the track. Actually, this one is the one that is generated by default for the event display inside the lariat. And this line is shows, the purpose of this line is shows where the interaction happened. And if there's a software that you can click and see the distance and whatever. So that's why they put this grid here. And it's got, for the image that I took from it and put it here, it's not clear that this is the separate line. It's not belong to this. Right. But if you see this, this is the electron line that then goes to shower. But here is a start from electron, shower. Right? So the purpose, I just put it here to see the challenge. Even with I, we have problem, but we trained a network and it did awesome separation between electron and pi zero. That's why, people turn to use this stuff to do physics. Gerson, everyone has lab 3 now? Could you guys check if you have lab 3? You should have it.
I had a quick question. So on 2.4, this is the one where we're loading up like an actual data set. When it said there was the different, let's say the different indices. So it had the readout planes and then the wires, and then those samples of the wires. So those values from the samples, are those just the charges? Okay.
Yes, the charges, the energy. Do you see ENG there? Let me open my lab. So this is the event number, how many events we have inside the file. And this is two-plane induction collection. This one is the wires number. We have 240 wires in the lariat detector with 2 planes. Okay, and this is the actually drift time.
Right. So is that 1 microsecond use each sample, or is that?
Is microsecond.
Okay.
Yeah. Actually, it's the drift time. Yeah, it's microsecond. Yeah. Okay, but unit or
I was just
number of
wondering,
data that we
I
have.
just was wondering, is that, so we have 4,096, so it's
Yes.
over time?
Time,
Okay.
yeah. And I think it's designed based on the event that it's defined in the detector. For example, different, group have different definition for the events because the events come nanosecond, microsecond. It's definition of where they can take the event. So they said that, okay, the start time is here and the final time is here for one event. So they're seeing the events inside the detector. And they store it, name it event. So everyone has lab 3? Did you check? You don't have your laptop? Did you check it? I just want to.
Can you refresh your browser?
Oh, and reload it and see where it's, trolling.
No, it's not work.
So as I said, I generated 1 million of each particle, 1 million events of each particle, and we store them in H5 based on what information we need for the, analyzing the data. So we change it to H5 and put it in this direction. So if you try this, you get huge amount of files. And if you look at the files, it starts with the particle name, for example, electron, and the anti-muon, and other things. So there are many ways that we can load the H5 files and see the file. So this is one way, which is called globe. So with globe we get the files in this way, and if we print out the length of the file that is taken in this line, we see we have this much 6,745 files. And if we print file first element, it gives us the first file among this. And then so each file is contain events. Some of them has 500, and some that you saw in previous lab, it has 2,500. So we can, and then as Joe asked, see that what's inside the file. We have information from wires in different plane, in different time, drifted time. And also the Monte Carlo give us more information about what's going on inside the detector. We can separate and have the separate interaction as a specific interaction generated with Monte Carlo. So for example, for the neutrino, we specifically produce CC, which means charge current, with the mediate particle with its charge particle, W plus and minus. And we produce also NC, which is neutral current, which is the mediated particle is neutral WT. So then I just want to say, okay, so we have 6,005 with different names, which specify the particle, the information of particle inside the files, the name of the file. So we should get the name and tell that this is the information inside this file is this particle. So this is the way that we are loading the file, and then the name before underline is the name of the particle. So we are grabbing that, and then if we print it, we see that we are getting the information for each type of particle with the first file with that specific name. Make sense? And now if we open up the file, for example, with the PyPlus, the first PyPlus file, it's H5 file, so we need to have H5i to open the file, right? So if we open it and see inside of it, it's 500 events, 2 different planes, 240 wires with 4,096 drifted time and samples. We call it samples. So we save this information inside the feature. This is the element inside of NumPy. If you look at lab 2, you see that this is a feature. This is one of them inside the NumPy array here. And also this is the other, these are other information that I save because we're gonna use it for training. For example, I save the energy of the incident particle, so we can do the regression and maybe train the network to tell us what's the energy of incident particle, to see the image and tell that this is the energy of incident particle. So I put, for example, I saved energy information in the file also, and for some purpose we may need track lengths, and we have 2 different energy. One of them is for incident particle that it's not neutrino, and the E mu truth is the neutrino energy. And for the particle that it's not neutrino, this is like minus 99999. That you can see that it's not neutrino, even if you don't know the name of the particle. And the feature is the image. And this is the lepton as a result of neutrino interaction, the momentum of the lepton as a result of neutrino interaction. So we have Monte Carlo that can have the different energy. The input of the neutrino energy that I consider is just the flat neutrino energy, but we have different lepton momentum as a result of this energy. So we save that so we can see because we don't see neutrino in the detector, right? The only thing that we see is the result of that. So we're gonna, maybe train the system to distinguish between different momentum of lepton from different neutrino interaction of different neutrino source. And the mood is the kind of interaction, as I said, charge current, neutral current, and I think I save also for different pion interaction. But for example, elastic, inelastic, or whatever, it was possible. And PDG is the particle ID number, because we have in physics, PDG, right? The physicist knows. So we have different ID for different particles. That, for example, electron is 16. I don't know, made a mistake. Electron is 16. So if we put 16, it shows us electron. So there's some, useful information that it's saved in the file. And the image is just from the feature. And the exercise 3.1 is just create two directories, store total number of events of each particle type in one. Total number of, okay. So it means that I think all the electron goes to one file. And they store the number of events in each file in another. So the first part is just, I guess, store the total number of events of each particle type in one, right? Means that store all electron in one file. But I don't understand the second question. Amen. So the training part is, sorry, I'm just the first time I'm looking at. Yeah. We will use Matplotlib for most of plotting. So this is the one that didn't work, and I asked Grayson to see if he can do something to work it. So mine is not work. I want to make sure that not working.
You just have to import
Yeah.
H5PY.
Okay. Where is imported? I think I should start. Yeah, working. And you see the image. This is the. So it's open up the Pion Plus first file and get the feature and plot 1 to 1 means create 1 by 2 grid. Okay, so it's create 2 grid and the axis, and then the image file goes to first one goes to this first grid. It means induction, and the second one goes to this grid, which is collection. So they are same events, but for different plane, right? And it's Pion Plus. So I think these particles come, interact, and give 2 results. And so by looking at this, if you image like 100 different pi plus, you will get the idea of how pi plus should look like. I'm talking about the image, just image, forget about physics. How it should be look like inside the detector, right? So you'll get the idea. If you change different 5 different events, you will see different this kind of image, and you'll get the idea how pi plus look like. And then if you change the particle to electron, for sure you're gonna see the showering, right? Also for pi plus, pi 0. So you can train yourself by looking at the image and see what's going on with this particle inside Lariat detector. And one of the questions that here he told me that he asked about this question. That's why I go through that example and show that slides to you, because I want to make sure that everyone understands what it's showing in the detector, right? And then by looking at different images that you can produce in this step for different particles, you will be able to answer this question, right? And do go and try to see images as much as you can. Because he said that he's gonna explain again, go through different particle and the different classification. One of them I explained why we are looking at electron and pi zero separation, because they, look like each other. You can go ahead and see which particle looks, for example, look at pion plus, pion minus, and see the difference. Pi zero with photon, because I force also I generate photon directly. You can, because you have photon files inside. You can look at it and see the difference between photon, for example, and electron. Photon and pi zero. So then you can answer this question, and this is the homework, and also it's plotting. The plot is the following code presentation. I will look at them. Oh, okay, the downsampling. I think you go through this again. I just tried to introduce the file and what's inside the file, that you guys understand what's the image, how the image should look like, and what you look for, train yourself first. And then we can go ahead and train the system to separate that and see what's the efficiency to separate different particles that look like each other. Any question? And I think for the lab 1 and lab 2, we got a screenshot of your homework, your exercise and homework right before the class. I think the time is, done for those two. Yeah, just to start this. Any questions?
So the number of events can change depending on which image you're looking at, but everything else stays the same, right? You keep the same number of points.
Yes.
Okay.
Yes. Just the number of events might change. And I think it changes between 500 and 2500.
Okay.
Right. Yeah, because we generate.
I don't know which ones you included, but yeah.
I think, we have both. Yeah, we have both here. Yeah. So it has more, and but you'll see, just one by one, right? You want to see the events, first event, and then second event. Try to see the image of different events. And you can change the files, goes through the same particle, but in different files. You know what I'm saying? It's better to change the file. It's a practice. And the first one, I think it was just putting all the same particle in one file. And then you have a million events in each file. If I understand that question right. Any other questions? No? Okay. We're done. Thank you guys. I'm sorry if
Can you email me?
Emily?
Amir?
Amir? Okay.
That's not good.
Yeah.
So I can just do a quick right.
What I'm thinking.
I've got to get the kernel running, and I've got to
Well, I was just
put a
gonna
specific
put
call inside of the.
it's written right now.
Oh.
So I think 400 is real.
Oh, yeah. That should be good.
What if, what if, like, we're not doing everything, we're maybe like under gig, right? Like the data that they're dealing with.
Are you in the same class?
We just like have like a deep, I don't know if you want to like have like a subdirectory for class stuff. So worry about, you know,
Right.
this is the, is there another backup of this, or is this all in the morning?
Oh, okay, that's what you keep asking.
Or if you want the slides that I show you,